to our last section, which is going to be about reversible and irreversible processes and entropy. We're going to understand the term entropy and how it relates to the second law of thermodynamics. If you consider a box which has two different gases, this red one and this yellow one, then over time, they're going to mix up and become something like this, right? So there's an arrow of time going from this state where they are clearly kept separate and just the divider, imagine that a divider was here that's just been lifted and it goes to this mixed state. It is very unlikely that you are going to go from this mixed state spontaneously, which means without any external effort, to this state of them being separated. Yeah? Similarly, if you consider the coffee cup and the environment, then heat is always going from the coffee cup, hot coffee cup, to the environment. It's very unlikely that anything will come back. The environment will warm up your cup. So there's an arrow of time that we're going to talk about. So processes in general can be reversible or irreversible. Most of the processes that occur in nature are irreversible and are going towards what we call increased entropy or increased chaos. For example, in our previous one, this has a more chaotic state where the two are mixed together compared to this initial state where they are nicely separate. Okay? That would be an irreversible process. In order to define entropy, though, we need to define it on a reversible process. Okay? So a reversible process is one in which every state along the path going from some initial state to some final state, every state we can return along. Okay? So the entire process needs to be reversible, not just that we can go from that final to initial state, but we need to go along the exact path. So a reversible process is an idealization, but some real processes are pretty good approximations to it. We're going to talk about entropy, which was a term coined by Rudolf Clausius in about the 1800s. Yeah? Very important concept in physics and chemistry. So consider a gas in one state and it has some entropy S1. And we're going to move to another state, S2, which is our state 2. Notice that S1 and S2 are state variables, okay? So just like P, V, and T define the state, S1 and S2 also define the state. We define, normally it goes from this irreversible purple path from one to the other. We're going to also imagine a reversible path, which is this green one, where we're going to define the entropy change. So delta S, which is S2 minus S1, is going to be defined as Q over T. That means the amount of energy exchanged, Q, over the temperature change, or temperature. That will be my reversible process. We're going to say that the reversible and irreversible processes have the same entropy, although entropy is not really defined for the irreversible. But we're just going to imagine a reversible process, find its entropy, and say that that can be applied to the irreversible process, since we have no way of doing it for the irreversible one. So mathematically, delta S equals Q over T, where we have this little symbol R under the Q, which is reminder that Q for the reversible process. So its units are going to be joules, energy, per Kelvin or per degree Celsius. In MKS SI units, it's going to be per Kelvin, so joules per Kelvin. Okay, remember it applies only to a reversible path, okay, even if the system actually follows an irreversible path. Okay. So we talked briefly about the bird drinking, and I said that the perpetual motion machine would operate continuously without any input of energy, so Q equals 0, and without any increase in entropy, so delta S equals 0. Okay. But perpetual motion machines violate the first law, since then our first law would become U equals W, and you cannot keep on taking out work from just internal energy. So the second, and it also violates the second law of thermodynamics, which states that we're always going towards increasing entropy. So delta S has to go in the direction of delta S increasing. Okay, so perpetual motion machines will never be invented. They defy the laws of physics. There's another way of understanding entropy as a measure of disorder in the system. So if you consider that initial diagram I showed you of two gases, and then the more disordered state where they are mixed in, where there is greater disorder, there is greater entropy. So that's our natural arrow of time towards increasing entropy. And this comes from the concept of statistical mechanics. Okay, so we're not talking in terms of probability, which arrangement is more likely, the initial one with the two gases separate, or the one where the gases are all mixed in a sort of random fashion. Okay, so we're going to define entropy for that kind of system as S equal KB, natural logarithm of some W, where W is the probability of that state occurring. Okay, so probability of a particular configuration, say the disordered state versus the initial state, or actually compared to all the possible configurations. KB is the same Boltzmann constant we've seen before. Do not confuse W for work. It's just the same symbol here, but it is stands for something completely different. Yeah? Stands for the probability of the configuration. Okay. So this gives the second law as a statement of what is most probable rather than what must be. So we see that now we're left the certainty and we have come to probabilities. The second law also defines the direction of time. We've talked about this of all events as the direction in which the entropy of the universe increases. So let's do a simple problem about entropy and then we'll stop. What is the change in entropy if 1 kg ice at 0 degrees Celsius is converted into water at 0 degrees Celsius? So if you remember phase change, yeah, that's what's happening here. All the heat that is taken in is going to go into melting the water and not increasing the temperature. So our delta S, which is defined as Q over T, the heat, and this heat is M times L, where L is the latent heat of ice. Yeah, M is the total mass, which is 1 kg here. So 1 kg times the latent heat, which you'd have to look up. It is 334 kilojoules per kg, divided by the temperature, which is staying constant 0 degrees. So we need to convert that to Kelvin, 273.15, if you like. Put that in your calculator, and you should get a change in entropy of 1.22 times 10 to the power 3 joules per Kelvin.